So any questions about assignment, which I believe is assignment number 3? I'll try to keep my chat open.
Let's see a question.
Can our arrays create arrays of arbitrary structures?
Yes.
Yeah, that's a very concrete and open question. So the answer is yes.
Yeah, it's templated. So yes, as long as the structure has a regular constructor, which means you can define that structure yourself. If you can use it, array can use it.
Yeah, it's one of the nice things that so I think you can ask Ransit for the details, but I think one of the nice things of his implementation is that it's mostly object-based. With templates, you basically are allowed to put whatever you want in there, right? Should we make an array of directions into arrays in assignment 3? You could, if you wish. I think that we are more concerned with the big arrays than small arrays.
Yeah. It's a small array. It's also a constant array.
Yeah.
Which means that writing some code to fill the R array is a little bit. It's making it harder than it needs to be. Okay, here's a good question. To deallocate an R array, is a.clear sufficient, or do we also need to use delete somewhere? Well, you never use delete, but there's two parts to an R array, if you think about it. It's the objects itself, which under the hood has like pointers and stuff, and then there's the data. So a.clear gets rid of the data, which is most of it. The rest is there, just as when you have an integer, you say int a. That is always there, but it stops being there as soon as you exit, say, either a function that uses it or in main. So yeah, so okay, good.
For whatever reason, I lost my chat again.
Another question is.
Can you comment on?
Yeah.
Oh, yes. So can you comment on how are we expected to use .data method in the assignment? Well, it's mostly for accessing the values of the arrays elements, right? And to be clear, it's pointing to the first element of the array object.
So once you're done with the assignment, there really shouldn't be any .datas left, because you can pass arrays to functions. But you already have some functions from the previous version of the code that doesn't expect arrays, it expects a pointer. So in an intermediate stage where you might still have some functions that take a pointer, but some that take an array, you could use both if you want to. If you don't have to, you can just switch to array all at once, but then you're changing all of your files all at once, which is a bit much. By doing so, you could change one file to take arrays, and that will not use any .datas, and another module to not have changed yet, so it takes pointers. To get those pointers out of your array, you use the array.data. Okay, so that converts it to a pointer, and has all the trouble with the pointer that a pointer has. It doesn't know how big it is, but that's how you get a pointer out. So if you need a pointer at some point somewhere to the first element, then you use data. If in the way you do the assignment, you never get to that point, you don't use .data. Yes, you should change all of your modules to take arrays instead of pointers. But if you're doing it step by step and with intermediate commits, you don't have to do it right from the start. You could do it incrementally.
Okay. Any other questions? Right. So if there are no more questions, we can still take some questions at the end. But if there are no more questions, then let's start with the lecture today. I'm trying to do full screen, so hopefully you guys can see the slides full screen. Let me know if it's not. So what we're going to be talking about today is file I/O, and with file I/O we mean file input output.
Marcelo, there's no full screen. We see
no full screen. What are you guys seeing?
We see the bookmarks and your
okay, 1 second.
slide.
Okay, thank you, Francis. Let's try this again. What about now? It's good? All right. Thank you. I'm sorry about that. So I was saying what we mean with file I/O is file input-output operations, means any kind of operations related to reading, writing, accessing data, storing files. We're going to be talking about these kind of operations. We are going to be talking about data management related in particular to metadata. And then we're going to be talking as well about file formats, different file formats. And I keep losing my chat screen. So why this is so important? Well, there are a couple of reasons. Some of these reasons will come more clear next week when we're going to be talking about performing or performance. But the truth is that in any program, in any computation, in any work that you ask the computer to perform, the slowest part is still writing or reading data. And the reason is that interaction between whatever it is, all the logic, all the instructions that are being executed by the processor and the access to the data that is stored in a different physical device. So for understanding this a little bit more, we're going to have a very quick digression into the file system. The file system is basically where we keep most of our data. In many cases, this has changed lately, especially for desktops, workstations in our offices, and even laptops. But in most cases, and especially in supercomputers, the typical situation is to find that the data is stored in a spinning disk. And so this has changed because nowadays most of the computers has SDS, which is a SSD, sorry, which is a solid state devices. That of course improves a lot the speed at which we can read data from these devices, but it's still, in spite of that, it's still the slowest part in any computation. Of course, in the file system, we have logical structures that not necessarily match the physical structures that are in the hard drives. We have directories, subdirectories, and files. We can even have repositories lying on top of that, or other kind of organizations. The important thing to bear in mind is that on the disk, these are just blocks of information, blocks of bytes. And sometimes they lie just one next to each other, so consequently, or in other cases, they do not. And for instance, in some operating systems like Windows, even on Linux, you may have programs that help you what is called defragment the structures of the files, meaning putting all these blocks together to each other. So when they are being read by the file system, then they can improve the performance. The other important thing to consider is each input-output operation, usually refers as IOPS, gets hit by latency. And that means how much time the file system and the operating system need to wait until the data start to flow. So this is another thing that affects seriously all these times that are starting to be aggregated and then affect the whole process of reading, saving, or accessing data in any needs. So what kind of input-output operations, or IOPS, you will hear many people saying, well, what is the rate of IOPS or things like that? What type of operations are related with? Finding a file, for instance, if you issue the ls command on the shell, basically a lot of things happen behind the scenes. First is ls, and this happens at the level of the operating system. So ls will check if the file exists. If it exists, it will read the metadata, meaning the file size, data stamp, who is the owner. If you are in an operating system like Linux or Mac OS, it's going to check, and even on Windows, I believe nowadays, it's going to check if you have permissions for accessing the file, if you have permission for reading the file and displaying information. Opening a file, well, implies checking that the file exists. Opening, if it is allowed, again, if you have the right permissions. If depending on what your program is doing, possibly create the file, and then find the block that has the first part of that file in the file system. So basically, think about pointers again. What happened is in the file system, there is a function called FAT, F-A-T, is a table that basically has pointers to the beginning of each file located in each place on the hard drive. It can be actual files, directories. If you look at Linux structures or file systems, it's also a file. And many other things are considered files. So all that information has to be there. Reading a file basically implies positioning the pointer in the right spot, reading that block, take the information out, and then find the next pointer to whatever is the next block. So again, things that usually are given by granted may imply more operations, more steps than what you may consider. Write into a file, very similar in the sense of reading, but check first of all that there is a space on the hard drive. Find the position to say the next chunk of data, and then basically write the block or the data. Many things are repeated while we read or write, expanding on multiple blocks or chunks of the data that can be saved on the actual physical device. Basically, moving the pointer, sometimes referred as seek. Basically, the file system must check that we are on this where the data is. And finally, this is quite important, closing the file. In many programs, if you don't close the file, your files will look corrupted and won't be able to recover the data. So this is just a few of the operations, the most common operations that are related to IOPS. One of the things that you might notice is some of these operations underneath have other operations, so expand a little bit more. And these things are expensive because in terms of some of the operations like seeking the next pointer or moving the reading head of the hard drive implies many mechanical devices, mechanical operations. And again, these are still the slowest part in our computers. By the way, feel free to ask any questions. Many of these concepts are quite common for us, and other concepts maybe not so. So feel free to ask any questions. So this tries to summarize a little bit what I was mentioning before, but with numbers, why reading or accessing data or IOPS in general is still the slowest part of any computation. And what you see here is on the x-axis is years since the 1950s, late 1950s, and then the access rate in megabytes per second and how it has increased in a log scale. And you can see the red dots are basically the speed at which we have been accessing data from hard drives. This is just pure hard drives, I believe. I don't think we have any SSDs there. But then what you see on green, this trend, this slope that shows the green arrow is the rate of performance improvement, in particular in supercomputer systems, measures LIMPAC is a particular suite of tests that is used to measure how fast a supercomputer can run things, can compute things. And you can see the slope is quite different. The slope is much more steep in the case of the performance, meaning that the speed at which we compute things is way faster at the speed at which we can save things. And that is why we say that file I/O or IOPS in general is always the slowest part in any computation, in any program. And that is what is also the consequence of being file IOPS, the bottleneck for the programs. So we're going to see again some of these things again next week when we talk about performance, but also when we start talking in the last part of the course about high performance computing, we will see ways to mitigate that and how this is affecting programs running in supercomputers in particular. But again, what I want you to take from this plot is, okay, even though a speed of accessing data from hard drives has improved a long time, the speed at which we can compute things are way faster, and that means that saving data or accessing data from hard drives is still the bottleneck in our computations, in our programs. We will see also when we talk about high performance computing that usually we can classify the programs or divide the programs in categories depending on what is the most demanding part of the program. It's the computation, it's the communication between different elements computing things, it's saving data, it's accessing memory. But we will discuss this a little bit more later. In any case, as I say, IOPS are still and will still be for foreseeable future the slowest parts in any program. So that's why deserves to take particular care of this and pay particular attention to any kind of file IOPS. Okay. So what I have here is some recommendations on the same lines of best practices, but now is in terms of performance tips, if you wish, things that one needs to be aware. Of course, every time that we compute something, we want to store that, right? The best solution will be, okay, compute, don't store. Well, that won't work, right? We need to store our results, otherwise it will be meaningless to have computers computing anything. So how can we mitigate or reduce as much as possible the hit that we take by using IOPS? So one of the first things that you should consider, and we're going to be talking about this today, is saving your data in binary formats. It's way faster in terms of performance. It's way, it uses way less space, so reduce the size of your files compared in particular to text files or ASCII files. If you are dealing with parallel code, try to use parallel I/O. We are going to see this in more detail in the last part of the course. Maximize the size of the files, meaning try to have not 100 files of small files, but try to have, if possible, 1 or 2 big files. This is particularly important in high-performance computer systems or supercomputers like Niagara or Teach, because basically what happens is the block size in the hard drives is the smallest or the discrete unit in which you can store information. So if your files are such that the granularity of that is not too good, then you end up wasting a lot of space. If you came to the intro to Niagara, you may have noticed this in the difference between the home system and the scratch system. So bear that in mind. Having large block I/O is optimal on that regard. I see a question. I thought using multiple nodes on the same disk slows down the procedure. Okay, it's a good point, Beran. So multiple is a good point, and this is a particular issue with parallel file systems. What happens with parallel file systems is you have multiple processes, not only accessing the same file, but accessing the same directory on the system. The directory is locked. So let's put the example of 2 or 3 processes to visualize this, right? So if you have 3 processes trying to save data at the same time, if process number 1 starts the process of processor number 1 starts the process of basically saving the data, it will lock, and process number 2 and 3 won't be able to access the directory until processor number 1 is done. Now, this can be considered in parallel, but basically what happened here is the processors are not coordinated between them. When I mean parallel I/O, I mean a more sophisticated approach. We're going to be talking about NetCDF today and HDFI, which are a standardized way to save data. Those are libraries that are accessible, and they have parallel implementations on them include. So those things can take care of that. There are different strategies. You can have a head node taking control of all the input of the information on the file or recovering the information from the file, but other nodes providing the data so that it is basically cascaded by down, or they can basically schedule the way in which they save data. So different strategies. You are right. If you have multiple processes that are not coordinated between them, trying to compete, and again, I repeat this is important, not only for the same file, but different files on the same directory, they will lock that and they will be decremental in the performance, in the I/O performance. But if you have one implementation like NetCDF or even MPI I/O, then you are in good shape. Then the way in which the files are accessed and saved are organized. Okay, so it's a good point. No problem. I think I mentioned this, maximize the size of the file, but also minimize the number of files, goes basically together. It makes the file system more responsive. Again, these things are very important for parallel file systems in supercomputers, but at some point you may notice these things depending on how much work you do in your computers and how fast and new your computer is. You may start to notice these things again also happening in your system. What things don't do? Okay, so some of these are basically the opposite of what we say to do. So for instance, don't write lots of ASCII files. This is very slow. It wastes space, a lot of space. I will show you some numbers. Don't write many hundreds of files in a particular directory. Is basically called file log or path log, as I was mentioning before. This is important. It may sound silly, but don't close files between small reads or writes. Basically, open a file, do all the things that you had to do, and then close it when you're done. Remember, closing a file is not just closing the file. It implies a lot of checks that the operating system has to run behind the scenes. So it's always good to try to optimize this workflow as much as possible. These numbers are particularly good for the Teach cluster, I believe, but also for Niagara in general. Don't write many small files. Small files in this case is smaller than 10 megabytes. These kind of systems are optimized for large block I/O, so try to increase the file size as much as possible. And again, many of these recommendations will apply, and you will benefit of using your own systems as well. There is another problem. We're going to discuss this a little bit more. Another issue when we save data in ASCII format, and I'm going to talk a little bit about more about that in a second. But before that, let's review very quickly what type of file formats we know or we can save data into. So one file format that everyone is familiar with is ASCII. ASCII stands for the American Standard of Code Information Interchange, and it's basically plain text. Anything that you see like source code, TXTs, Markdown documents, that's all plain text. And we need those for basically writing code, for instance, right? It's not that we need to not use them. What we try to avoid is using them for saving data that is being produced by the programs, especially if this large amount of data, right? If you are talking about electromagnetic field that is being computed around a particular place or situation, then probably you are better using other file formats than just plain text to store that. An alternative file format, which is recommended and suggested for saving actual data, is a binary format. And binary format, what it means is information, numbers, for instance, encoded in basically machine code. Machine code, if we go to the very basics, it's just zeros and ones. It's binary, right? Is there current or not going through that circuit, that kind of things. Of course, machine has a better way to store that information. It's called hexadecimal system. And basically what they do is they use a system based on 16 digits from 0 to 9 and then A to F to store that information. And they have some more flexibility, but this is basically not readable for human beings. You need to have a hexadecimal converter in your brain, sort of. But basically, that way of storing the information is just dumping how the computer sees the data. And it has advantages and disadvantages. The other thing that is important to consider associated to data is what we refer to metadata. So metadata is all kind of data related to the data. For instance, if I'm using a program, what version of the program I use? If I'm using libraries to compile my code, which version of those libraries I use? Even the flags I use for compiling the code, we're going to see this again later, the optimization flags that we can use, or the linking flags with the libraries. The initial conditions that we're going to use, think about the ants on table, how many ants we have, did you set the seed, what was the value of the seed? All that kind of information that allow you for reproducible results or recovering the results that you run once should be part of your metadata. Some people like to say it's like the notebook or notepad, that like actual notebook that people used to keep in the labs when reproducing experiments in the actual labs, in the wet labs. Well, that's that kind of things. Other file formats may involve databases. We are not going to be talking much about that here because it's not really something that is quite used on scientific applications. In some cases it may be, but not the majority. And finally, we have some standard libraries. So standard libraries, for instance, like HDFI or NetCDF, which it has a lot of advantages of being used over other formats. And we are going to discuss a little bit about them today. So let's go to our first two file formats, ASCII and binary. So as I told you, ASCII stands for American Standard Code for Information Interchange. And then we have binary, which can be think or thought as a native binary. That's basically the code that the computer sees or understands with respect to the data. So what are the advantages and disadvantages of one versus the other? Well, if we look at the ASCII or plain text formats, one of the advantages you may argue is that it's human readable. So you can open a file and see with your bare eyes, basically, what are the numbers, what are the values stored there. Some people may argue portability. This has to be taken with some considerations because it depends on the actual architecture. So for instance, if you save a text file, maybe some of you have seen this already. If you save a text file, a source code in a Windows machine, and then you copy over a Linux machine, you will start to see that there are some discrepancies, for instance, in the characters used for the new line. So it's true, it's a minor thing, but still there are some discrepancies sometimes. What are the cons of using plain text? Well, I told you it's very inefficient storage. Basically, for every single character representing a value, you are basically using a byte for representing that. It's expensive for read and writes. And this is the other reason I didn't mention before. Whenever you have data, in particular numbers, and you want to store them as plain text, what happens is the computer has to convert them. So you basically take the number that is in the memory, think about an array, as we were talking at the beginning of the class, or any array, or even a variable, right? A float variable. It will take that number, and it has to convert those values into a character representation. So there are two things there that are not good. One is the time that is being spent in the conversion. So that's not for free. It's not like taking the values and dumping into the file. There should be a conversion there. So I need to go and match the value I have with the character in the ASCII table. The other thing that is bad, that's one of the things. The other thing that is bad is that we lost precision. So if we are talking about a very long float, there will be at some point a truncation error in the conversion. So basically, if you need precision, if you want to store your results as they are, you need to be careful with saving the data in ASCII because you may be losing precision. You are basically saving results that are not accurate as they were computed on the machine. Okay, so two things to consider there as disadvantages. Now, if we go to the other side, to the native binary, what are the advantages? Well, the advantages is it's very efficient in terms of storage because there is no, basically the computer can use this hexadecimal system I was telling you before just to store the values, and it's more efficient in that regards. It's very efficient in reading and writing because there is, first of all, there is no conversion involved. And basically when we're talking about binary is whatever values are stored in the memory of the computer take it as they is and just dump it into the file. It's brutal, it's just like that. So, but this make it very efficient. What are the disadvantages of this, of course? Well, there are two disadvantages. First of all, if I want to recover the information that was stored in the binary file, I need to precisely know the format in which was stored on the memory. What I mean with this is, imagine that I have a million elements of numbers, and they are saved into a binary file. Now, these million numbers can represent a one-dimensional 1 million elements array, or it can represent a two-dimensional or a matrix of 10 by 10,000 elements. I don't really know unless someone tells me which is the structure. And that the native binary formats can tell you that. So you need to know a priori what is the structure of those elements being saved. The other disadvantage is portability, believe it or not. This is a less common thing, but in the early times of supercomputers, there were different ways to represent floating points. It was called endianness. So there are little endian and big endian representations for numbers. This is a minor thing nowadays. It's something that it may still be present in some architectures, but it's a quite minor thing, I would say. So this is a comparison between ASCII and binary, okay? Now, I was telling you, just to demonstrate this a little bit further with numbers, this is actually measuring an old system, part of the, or what it was part of the DITCH cluster before, the GPC system. So let's say that we want to say 128 million doubles or floating point numbers. And this, you have here different file systems. So the Scratch, basically, that you are used to. This is a way to save data directly into RAM. And then this is another hard drive. So look at the numbers. So the first row here represents the time consumed for saving this amount of data in ASCII format. And the second row is in binary. And you can see there, they are easily, in some cases, 2 orders of magnitude difference in how speed was to read or write the information from the hard drives using ASCII versus binary. So that is what this is trying to represent. We are talking of order of magnitudes difference in speed, and not only in speed, but also in size when you say data in binary versus ASCII. Okay. You can run this test with yourself. Now, just to convince you a little bit more, I have an example here of how different it is to say data in ASCII and binary. So, and we have here different languages, C, C++, and Fortran. The first row is how you will say the data in ASCII. The second row is how you will do in binary. There is no real difference. I won't go into details, but there is no real difference. 2 lines of code for each language, for each implementation. So there is no real excuse for not saving your data in binary, I would say. The only actual argument that sometimes I get when we're trying to convince people to use binary instead of ASCII is, oh, I can look at my data. And I can tell you, when you are dealing with 1 million numbers, are you going to be staring at the screen for the million numbers? No, you're going to probably use another tool for visualizing that, maybe a visualization tool or something like that. Well, same thing you can do in binary. So there is no real argument for not using binary. Some people use tests for testing and debugging, and yeah, sure, that's fair. Like, you may be looking at those numbers because you know a special case, you may know what the result to expect. But when you're in production mode, when you're running simulations, long-term simulations, there is no real excuse, and it will pay off long-term. Okay. Any questions about this? All right. So let me talk a little bit about metadata then. I told you metadata is basically anything related to the data, how the data was generated, anything that you may need to basically reproduce that data. You will say, well, in principle, if I have my program and I have the initial data that I use, the initial conditions, initial values, then, well, that is also part of the metadata. But think about now how you generated the program, which version of the libraries, which version of the compiler, which version of the program you compile for generating that. So anything related to that should be allowed into the metadata. Now, as you can see now, there is no room for you to say this as part of the files, as we were discussing before, either ASCII or binary. So there are some auxiliary formats like XML for saving that metadata. What we're going to be discussing next is some binary formats that can also allow you to include the metadata as part of the file, which is very convenient, but also they are self-describing, meaning the problem that I mentioned before of not knowing if 1 million numbers came from a 1-dimensional array or a 2-dimensional array can be solved in that way. Okay. So, by the way, this is an example of how a metadata file may look like. So XML, this is a way, it's very used in websites as well. It allows you to store data with encoders, like, for instance, which format, which version it is. In this case, it's something related to an image, when it was generated, the location, and so on. So just an example. So this is another variant of storing metadata. If you wish, you can generate this kind of files. But again, what I'm going after here is instead using these standard formats like HDFI or NetCDF. So there are different standard formats. This may be dependent on the particular field in which you work. But HDFI and NetCDF, HDFI stands for hierarchical data format and NetCDF for network common data form, are very well used and very popular across many different disciplines. Which are the benefits of this? Where they are provided by libraries. So you don't need to basically do anything else than just install the libraries, of course, and learn how to use those libraries. They are self-describing, meaning that the metadata can be embedded with the data. Of course, you will need to fill that part, but you have the freedom, you have the choice of basically putting your metadata together. They are binary agnostic, so they are portable. So that problem I was telling you before about endianness is basically covered by these different formats. Yes, XML is ASCII file, but remember, metadata doesn't mean that it's going to be million numbers. It's going to be just a few parameters, hopefully, and details about how you generated the data. So yes, you're right. XML is plain text, it's ASCII file. So, but if you use one of these ones that we are talking before, or we're talking right now, sorry, then you don't need to use the XML file. But yes, you're right. Again, my suggestion will be don't use ASCII files for when you have large amount of data. Sometimes we need the ASCII files. Examples of these are the source code. Examples of these are a tiny file where you save all the initial parameters of a simulation. So those probably will not make sense to store in binary formats. Like, let's say, even if I have 50 parameters in my simulation where I need to control different arguments, different values of the variables, I can still store it in a text file, because then I have the power of using different tools to modify that on the fly, right? What I'm talking is about when we save humongous amount of data that is being produced by the program. And the metadata is one of these cases where it's very common that the data is not large. So it's mostly just a few kilobytes, maybe, no more than that. Okay. What are other benefits of using the standard formats? I mentioned the self-describing ones, binary agnostics. Many of them support parallel I/O and native file system support. So what it means is, what we were talking at some minutes ago, is this possibility of having different processors or processes in the program writing in parallel the data. So that is well organized by these libraries. And on top of that, there are broader tool supports. For instance, there are visualization tools that you can use to visualize the binary data. So it's very friendly in terms of the users that you can get from these file formats. Okay. So we're going to talk in particular about NetCDF. If we had time, I have a few slides about HDFI, but we will see how it goes. So basically, it's a format as well as an application program interface. What it means is it has the definitions of how the data will be stored, but also offers several functions to help the user, meaning us programmers, to store the data or our data in that particular format. Basically, you don't need to know the low-level binary formatting. The NetCDF will do the interface for you. It's suitable for many common scientific use cases. And if not, if you need to store something different, HDFI probably is a good complementation of that. There are a lot of examples and documentation available on this website. I just learned they had also a Git repository, because they also have bindings for different languages like Python or R. So I may add that repository or put in the links on the course website. But basically, I think hidden somewhere here, there is also the link to the Git repository. Okay, but again, it's a really good place to go and look for examples. How does it work? Which is the data model behind this file format? Well, of course, we are going to store data in binary format. So that is going to be part of the model. We are going to also give a type and a name. So what I mean with a type is, think about an array. It will have a particular type, for instance, integers or floats. Then we'll have a name, how we identify that object within the file. Then this is something that is interesting. We have dimensions. So these are the dimensions associated with the object. It can have one dimension or multi-dimensional objects. And then it will have names associated with these dimensions, meaning that if I want to use these dimensions as well for other objects, I can reuse them. And this is just one unit in the file. Then I can have multiple of these units. I'm sorry. We can have, this is very interesting as well. We can also have attributes associated with this object. What can be those attributes? For instance, units. If you are working on physics, you will know that units are everything, right? You need to have units associated with your quantities just to know, okay, which units I'm measuring something. in which units are measuring the energy, in which units are storing this particular value. So those attributes allow you to specify which units you are using, for instance, right? And this is one logical unit within the data, the file format itself. Now I can have multiple of these, but I can actually reuse some of the things. These dimensions can be also used in other objects or the attributes as well. In addition to that, I can have file attributes where I'm going to store, for instance, metadata associated with this option, how these options were generated. In addition to that, I can also have dimensions, global dimensions for the file, and then instead of storing, let's say that each dimension is the same for this object, instead of storing them locally for this object, I can have the objects pointing to these dimensions outside of these logical units. Okay. And finally, of course, I will have a file name to identify this object. But basically, this is the abstraction layer of how a binary NetCDF file will look like. Okay. Important things to remember from here is all the flexibility that we have associated with this object. So this is going to be representing a variable, most likely some sort of array, high dimensional array if you wish. There will be dimensions for this array. There will be the name of the array, the type of the data, and attributes associated to that, as well as attributes associated to the particular file, which can be or are going to be basically the metadata. So in that way, we had the data, we had information needed for recovering the data, that this is where we store basically the structure of how the data was encoded and shaped, but also attributes that can tell us a little bit about the data, but also attributes that can tell us a little bit about the process in which we generated the data. Okay. So how we do this? A few more things. I think many of these things I mentioned. There are lists of conventions that you can follow for variable names and unit names. So for instance, words like cm or centimeters English or in American or British English are recognized. Basically, it's a way to allow for exchange of information between different codes. So if you have collaborators working in the same discipline as you do and you want to exchange information, if you both use NetCDF, that's an easy way to basically guarantee that you can basically communicate your results with others. There is a long list of conventions, again, from the same website I was mentioning before. So you can follow those conventions just to standardize even more your formats. Okay, so let's see how are the steps of reading and writing. And some of these steps are going to kind of resemble the steps that we were discussing about file IOPS before. So the first thing is we're going to start by creating the file. We are going to define the dimensions, and we're going to define the variables. We are going to end the definitions, write the variables, and close the file. So basically, in the code that you're going to see next, all these steps are going to be followed in that way. For reading the data, it's very similar, but we are going to start by opening the file. We are going to get the dimensions IDs. We are going to get the dimensions length, and then the variables ID, and then finally read the data. The reason why we need all these steps is basically to avoid any kind of confusion with the structure in which the data is stored. And it's related to this metadata or internal metadata that is being stored in the NetCDF file and allow you to recover the whole thing. So let's see how a code looks like. So in this particular case is for writing the data. So we're going to start by including some of the standard libraries, but then the new one is NetCDF. I'm going to do something called a macro definition here. This is a way to define a function. I don't remember if we had seen this before, but this is a way to define a function using what is called a ternary operator in C++ or C. The name of the function is min, so I'm going to compute the minimum between two numbers, x and y. And what I say here, if x is smaller than y, then return x. If not, then return y. So it's a one-liner function defining a macro. That's right. That's right. This example, I have other examples with C++, but these are C libraries. So then we're going to just define n, and n is going to be the number of points we're going to have. We're going to define some other variables. Many of these variables you will notice are just integers because they are just flags used for getting a handle of how the operation was performed. So NCID, variable ID, and status are these kind of flags. Then the dimension ID is a two-dimensional array of basically 2 integers, and then a pointer, basically data is a pointer of integers. This is a C code, as you can see, also wrote because printf, overall from printf, I'm using printf here. And I'm also allocating memory at the old style. So I have another example with a C++ code. As I say, your friend here is the Unicar website. There are tons of different examples. This one is taken from there. And I just wanted to show you the basics here, and then you can extrapolate or look at the other examples for more details. So what we're going to do here is we're going to fill this array basically with the minimum of a given expression. In this case is a subtraction of the absolute number of the remainder of the index divided by n and subtracting 2, just an arbitrary value. Think whatever operation you want to do to fill that array. So that's basically what we're doing here. In any case, this for loop here represents just simulating data of any kind. It can be random numbers if you wish. Doesn't really matter. We have the data. This is the part at the status here when we are assigning status to a given call, where the creation of the NetCDF files begin. So the first thing we're going to do is we're going to call nc create. This is the NetCDF function create for creating a file called text.nc. That's nc is the convention usually used for NetCDF files. Then you have a couple of options here. nc_clover means that the file can be overwritten. So if there was a file called text.nc and I'm using the create, by using nc_clover, what I'm allowing the program to do is to overwrite the file. I can have another option called nc_no_clover. I believe that's the default if you don't specify it, I think. And that means that if the file exists, it will not overwrite it and it will give you a fail. And that's why you use a status to know if this operation was successful or not. Okay. The other flag that you see here is NC NetCDF4. That's the particular version of the format that we're going to use. Okay, so NetCDF4, I believe, is the latest one. So that's what it's telling you, is to store the data in NetCDF format version 4. Then the other thing that we're going to do is we are going to pass a pointer or receive a pointer from this function. The other thing that we need to do is now define dimensions. So if you go back to the diagram I showed you before, now each object will have a name ID, but also the dimensions and dimensions ID. So in this case, I'm going to call my dimension X. It will have 48 number of these, and it will be given by the dimension ID of 0 that is being specified here. Then similarly with Y, so X and Y will be, remember, we are storing a matrix here. That's what this data represents. It's a matrix, a linearized matrix as we saw in the ANS, for instance, but it has dimensions. So we need to know this is a 48 by 48 matrix. So these are my dimensions, X and Y. Now comes the definition of my variable. And my variable is going to be a matrix. So I'm going to use M. It's going to be NCInt. So what this means is NetCDF has its own type of representations. This is a little bit historical, but also a little bit to work as an isolated interface, let's say, with different codes or different languages. So NCInt is the way of saying, for NetCDF, this is an integer in whatever language. So we're going to see M is of type NCInt. It has 2 dimensions, and then we just pass the pointer to the variable ID. By now, we have all the elements that we need. We have the dimensions defined, we have the variable defined, so we end up doing the NCInt definition of the NCID. So these are the NCID identifiers of the object. How we put the data, we haven't put any data yet in the file. We just, basically, if you want to think about this, we have made the room, the space. That's right. And there are many others as well. That's right, Rob. NCFloat is for floats. We haven't put the data. How we put the data? Well, because this is integer data, we are going to use nc put variable integer NCID are the ID of the NetCDF files, var ID, and the actual variable. And then we just close the data. Sorry, we close the file. So NC close, NCID is what we call the handler of the NetCDF file, and that's it. Okay. We end up by freeing the data. Again, this is because we use malloc. So we are going to release the data, and that's it. So that's how we store the data. So much of the gymnastics, much of the things that we need to take care of happen when we define the dimensions and the variables that define the dimensions. Okay, putting the data is just one shot, but basically needs all the things to be in place before that. Okay, let me show you very quickly how we read the data. Again, in this case, I'm going to just include NetCDF. I'm going to define a maximum here because I want to compute the maximum for no real good reason. I'm going to have very similar variables to the ones we had before, plus the maximum that is going to be initialized at 0. And then the operation goes as follows. I'm going to open my file instead of create. So NC open. Because I'm opening, I'm not planning to write any data. I'm going to use the flag NC no write. And I'm going to pass a variable. And because this is C code, as you can see, I'm passing the memory. So it's passing by reference this variable. So that variable will be updated with the pointer to the file. And then the other function I'm going to use is inquire dimension ID. So for inquire dimension ID, I just need to know how the dimensions were called in this case, X, Y. So I'm going to inquire for the dimension ID of whatever was called X and Y from the file ID, the pointer, the handler of the file, and then put that information in my dimension ID vector, 0 and 1. Then I will inquire about the dimension itself. I inquire about the ID. Now I want to inquire about the dimension itself. So I want to know how many values, and I'm going to put that information in an X and an Y corresponding. Okay. Finally, with an X and an Y, what I need to do, because again, this is C code, I need to store or allocate memory for reading the data. And it's going to be an X times Y times size of, and in this case, they were integers. So that is my allocation for that. I'm going to inquire about how the variable is called, variable ID, and I go looking for M, which is the name I gave to the matrix, and that is going to be stored in variable ID. Then I'm going to get the variable. So this is the analogous of putting variable by getting variable from the file handler from the variable ID, and put the data into the data variable. I close the file. And that's basically it. And then I just do a computation for the sake of doing the computation and printing the maximum value and release the data, and that's it. But again, these lines here are the ones in charge of just reading the data from the NetCDF file. Basically, there is an analogy between or homology between writing and reading the data. Okay, and again, as you can see, this is just plain C code. Now, you may wonder, and this is a valid point if you haven't thought about this, I need to know a priori how I call my dimensions, X and Y, and the variable. And that's true. There is that knowledge that has to be done and has to be passed. But if you happen that you don't know, let's say you receive this information or this file from a collaborator, or you grab it from the internet, and it wasn't well documented, the name of the variable, there are some tools that come with when you install NetCDF as a library. So one of these is called NCDump. So NCDump is a command line tool that comes with basically NetCDF, and it allows you to access this. So for instance, if this is a similar file, not exactly the same, but it has, so if I run NCDump-H is just for the header, so it doesn't show me the content of the file. And this is a file called data.nc. Basically, I have access to say, okay, what are the dimensions? What are the name of the dimensions? What are the variables stores associated with these dimensions? And also look at the metadata. I have access to the velocity, which is in units of centimeters per second, or density and the corresponding units. So even when you need to know a priori some of the things, There are tools even on the command line that can help you, and you can even write your own in C if you wish, okay? But I just wanted to show you the very basic stuff. Other things, in addition to these tools that you can use, it allows for parallel I/O, as I mentioned before. This is something you may need to use in your assignment. Infinite arrays are possible, and the key is to use unlimited dimensions. Okay, so you will probably want to look at an example in the website with unlimited dimensions. We usually post an example just to guide you a little bit with that. And that is when you don't know a priori how many elements you want to store in the array. Okay, so I mentioned and I don't want to go into all the details, but there is a lot of information that you can store in the data. Who is the author of the data, when the data was created, version, operating system, blah, blah, blah. How we do that? Okay, let me show you. Okay, well, before that, I mentioned parallel I/O is possible to do with HDFI or NetCDF. We're not going to see that in this part of the code. Maybe depending how much we want to cover this, we may do it at the end. But the nice thing is that NetCDF or HDFI interface with MPI. We are going a little bit ahead of ourselves here, but allow you to do this in a very, very smooth and clean manner. I'm going to skip the HDFI as I told you, just for the sake of time. It's a very interesting file format to consider as well if you need something more that doesn't fit necessarily into the NetCDF data structure format. The nice thing of HDFI, the only thing I want to mention is you organize things in directory structure, sort of. So you can have, for instance, a folder, and within the folder, you can even store an image or data itself or different things. So it's a very nice, a very interesting file format to work with if your workflow requires something like that. Let me come to this at the very end. I just want to show you one more example of NetCDF. This is more C++ code, I would say. But the reason I want to show you this is just to show you how to include metadata. So again, it's going to have an example of how to generate some random data, given values, doesn't really matter. So this part here is to just generate this data out matrix. Again, it's a two-dimensional array, if you wish, fill in a particular manner, which is not interesting at all. But the thing is, I'm going to create a file using, in this case, NC file, data file. So that's the name of the file. And in this case, is using the replace option. So I can replace a file if it exists. I'm going to create the two dimensions by using data file now associated to the pointer of this file at dimension X and Y. I'm going to use the vector class here with NCDim, which is the class, the template associated with the class NCDim in this case with dimensions 2. And I'm going to fill XDim and YDim there. I'm going to fill my data using add_var, as we do before, with the data object, with NCINs and dims. And then I'm going to put the data using this pointer to the memory there. The thing that is new is how to add the attributes by using put attributes. And in this case, the field is going to be creation date and the date. Okay, and then I just return 0 for returning something. One thing we haven't seen yet is how to compile. I'm going to add the -i flag. And in this case, I have this environment variable, NetCDF Inc, for saying where the header files are located. The name of the file is just NetCDF writing CPP. It's not going to compile, just generate the object file, and it's going to generate with this name. And then the linking stage is the location of the libraries, the object file. We are generating the executable here, and we need the name of the library. So -l with the name of the library. And how you execute this, just calling that. When you do that, and you use the ncdown command that we saw before, and this is the name of the file that we generated, then you will see the dimensions, you will see the variables, but then you will see these global attributes, which is the metadata that we put in there, plus, of course, the data. Okay, so if you put the -h, you see up to here, you don't see the data itself. right? The other example I want to show you is just how to read the data. So very similar gymnastics as we saw before, but in this case, just we use get size and get dimensions from the data file object that we associated to the NC file. The other option is get var, and that's basically it. Okay. Now let me go back. So this is how you compile again. Nothing too profound about that. Let me go back to this summary box or summary table that we had before, just comparing the different file formats. So we talk about ASCII, we talk about the binary, and now the new column here is NetCDF. So the advantage of NetCDF is that it's efficient storage because it's binary, it's efficient in reading and writing. It does portability because it has the structure of the information stored within the file. It has embedded data. The only disadvantage that this is, it depends again on what type of data you are dealing with, is that it works only for multidimensional arrays. Okay. Let me see. I think we are past the hour, and I think that's mostly, I think the summary is something that we have repeat several times. My bottom line or last suggestion will to use these self-describing file formats. And basically this, along with other things, it will improve the performance of the input-output operations. Any questions?
I have a question, but it might not be totally relevant. I have issues deleting files when I'm working on Niagara.
Okay.
It takes too long most of the time, and like I have folders for each of my node, and I usually use all 41 for each.
It could be, I mean, it could be for different things, right? It could be, is this part of the same directory where you have these files, or are
they are the same directory?
Yeah, so you may be in the problem that we were discussing before, that if you are trying to access files within a given directory that is being logged. But if you point us to the particular files, we can take a look and help you with that. Deleting is not an issue for us. We can help you with that very easily.
I can do it later when you have time.
Yeah, my guess is that it may be something, it can be something transitory with the file system that is being hammered at that time, or, you know, if it is a really big file, it shouldn't be really bad depending on the file size, because the first attempt the file system will do is to prune the entry on that table that I mentioned before. But I don't know if it is a corrupted file, perhaps can run into other issues. Hard to say without seeing the details.
Okay, so I need to like submit a job just for deleting my folders and files.
Right. It could be that there are too many, and then that is making the file system struggle a little bit. But it shouldn't take, you know, I have prune directories with tons of files, and it, you know, but yeah, sorry, I don't know, maybe Rancy has other advice about that, but I can't tell much without knowing exactly the.
Okay, I will show them to you once we have time.
Yep, for sure.
Yeah, we need to know exactly what files they would be.
All right. Okay. If what are sorry, Rob, I missed that. What are the applications use of HDFI? As I say, HDFI is very rich file format in the sense that you can basically store anything. So anything that is no multidimensional arrays can go in a HDFI format. And one of the nice things is people like to think or see this as object storage solutions or object storage files, where, as I say, one of the things can be an image, another thing can be a grid, another thing can be even a database if you wish. So some people think about this as databases. They are not databases. I don't have any concrete example in mind other than just give you the general features.
So it's a richer data format in the sense that it can hold much more complex data.
That's right. That's absolutely right. So it can store, as I say, different formats. It can be seen as a mega file format if you wish, right?
So it's So if I understood it correctly, there's a file structure to it. So it's like a file of files.
You can structure in that way. That's right. So it allows you to do that. It doesn't necessarily to be stored in that way, but you can structure in that way. So the terminology goes as groups, and you can think about this as directories and data sets as files.
Interesting. Thanks.
No problem. All right. So I think that is it for today. Again, we are going to have the assignment posted later today, usually around 5 p.m. or so. And tomorrow we will have the office hours as usual. Okay. And if you have questions, you can post them on the forum or shoot us an email. All right. Okay, guys.
Thanks, Marcelo.
No problem, Rob.
Ramses.
See you tomorrow.